ставим. Мама, отец, гуляйте. Не замерзнет. У нас лекция начинается, мы хорошо доехали. Прекрасно все, очень хорошо. Сейчас Илья начинает работать. Мам, я не могу, извини, все нормально, просто. Давай. Прекрасно. Пока.
I would like to explain why, when we have established that structure of the sequence of derived accompanied diagrams, then we can have a criteria when the elements are not equal to 1 in the resulting group. So, let me recall that when we have the last derived diagram, then all these regions are actually of the same rank because all others were attracted to this in various steps. And then it will mean that every inner region will have many neighbors. We actually need only 9 neighbors to secure the hyperbolic structure, but actually we have a lot of neighbors for every inner region. Doesn't matter. As far as we have 9, so we have the convex layer structure. It means if we take this 0, the having a common edge will be 1, then it will be 2, etc. Then what happens that some regions will have the biggest distance from one particular region. And then it means that it is most of 2 edges of the previous level. Maybe it has 2 regions on the same level. Actually, it could be reduced in 1, doesn't matter. In any case, this is the part of the boundary without 4 neighbors. And then it should be very big, because if we have here the original region, then we look on the transversals, we have actually 4 transversals, so all this will be a very small part of the region, and the most of this will be on the outer boundary. Now, here we can do the same. We can consider the convex layer structure for the previous rank R minus 1. So it may be that it doesn't exist. If it doesn't exist, then this will be a very big part of the original relator. If it doesn't exist, then we look on the convex structure. Again, something is in the upper level, and then it also, for the same reasons, it has everything about 4. And then we proceed by induction. It means that ultimately, for some rank, almost a whole relator will be on the outer side of this diagram. It means that the word in the group is equal to 1, will have a very big part of the relator of some rank. Just cannot tell of which rank. It may be of highest rank or of 1 rank of this, which will be smaller. Doesn't matter. At least actually we could do it much more precise, but we do not need it. We have in some place a relator without for small pieces. And this is, small pieces are actually smaller. In other words, all the later is inside every word that it is equal to 1 in the resulting group. Okay, and then it gives us immediately a way to establish that the element is not equal to 1 if we have a word which does not have inside such a part of the related results for small pieces, then this word cannot be equal to 1. This is just a way to deal with this result after we've established the kind of the small calculation structure with generalized sense. And this is all, these are all standard tools as well. The main thing is establish the structure. When we have it, then we actually have a very easy way to proceed. So
not necessarily except for small pieces. If we have original region and only one layer above it, it can be 1/2.
yes,
Or only 1/2.
yes, yes.
But it's okay, but still.
Yes, everything is enough. Of course, you're right. Yes, but it doesn't matter. If we have a big part of the relator, not necessarily, not necessarily.
Not necessarily so big
Yes.
that you say, but at least 1/2.
Yes. Yes, but without small pieces, still doesn't matter. So, for example, we would like to understand why this group, if it has 3 generators, would not be reported for any class of inputs. So assume that x, y, and z are 3 letters. X, Y, Z are 3 letters, and consider the commutator x, y, z repeatedly. X, y, z, x, y, z, x, y, z for
How many times?
3 n times. The n is, I mean, the letter, so this repeats n times. So we have the commutator of weight 3n. But n is arbitrarily big number, And we would like to show that in this group, this commutator could not be equal to 1, which will mean that if we have a group, a free angular group with 3 generators, it will not be nilpotent for any arbitrary class of nilpotents. So I'm repeating it. Let me say it again. That we can write a word, a commutator x, then y, z, then repeatedly x, y, z, x, y, z, etc. n times. So we have a commutator of weight 3n. For n is an arbitrary number. I'm claiming all of these commutators for any n will be different from 1 in the free angular group, which will mean that it will not be nilpotent of any class of integers. So let me just so let me just make an explicit calculation of what kind of things we will obtain. Okay. So for this, let us calculate the following thing. Let A be some volt, and we have X, Y, no, I should say a contrasting color, excuse me, a contrasting color. And Y and Z. Okay. By the way, when we
להפסיק את המיזוג.
by the way, when we do make a calculation, it turns out that we never have cancellation in this world, never occurs. This is an easy recursive exercise. So in this we never have cancellations.
So, at all? What's A?
What is A?
A is a vote.
A is an arbitrary word?
No, actually we will first take the first commutators and add 3 new commutators, etc. We have just a recurrent way to consider it.
Okay, okay.
So this will be and I will already write it in the cyclic mode. Here is our starting point. Here we have y, then x, then A, then X, then A, then Y, then A, then X, then A, then X, then, for the first time Z, then X, then A, then X, then A, then Y, then A, then X, then A, then X, then Y, and then Z. Okay. So what we can see from this? Then if we take, for example, the next time, for example, we take a B, X, Y, Z, X, Y, Z. Okay. Then we will have this one as A, and then we can, instead of A, substitute the same thing as a whole this word with B instead of X. So we have a recurrent way to compute this higher commutator. So what we see here, A could be a long word. It appears here 8 times, and the sign always changes. Negative, positive, negative, positive, negative, positive, negative, positive. So the signs of A, just 1, negative, 1, minus 1, 1, minus 1, 1, minus 1, 8 times. Z appears here only 2 times. Y appears 4 times on this side and on this side, on this side and here around this Z, and X appears 8 times. So, and this structure will recur when we substitute this A by this word which is of the same. Then we have 64 B's, the appropriate numbers of X, Y, Z in each of them. I will have 2 Z's, 4 Y's, and 8 X in this, together with 8 B's, etc., etc., etc. So this will be roughly saying the structure of this commutator for any arbitrarily big n. Just repeat the same substitution n times until we have the resulting commutator. Okay. Now, if this word would be equal to 1 in the free angle group, then it should contain roughly a half, at least roughly a half of an angle relator. Now, but the angle relator has a well-known combinatorial structure. And the only thing I have to say is that these two kinds of structures are incompatible. Let me explain why they are incompatible. So let me remind the structure of an angle commutator. So then it was, for example, we assume that we have the commutator C, D, D, D 40 times.
Yeah, can you just write down the state?
Right.
You are going to prove
So,
that
okay, fine, thank you. So,
The word which will be appeared cannot be reduced via any single concept.
combinatorial structure of x, y, z, is incompatible with the combinatorial structure of an angle relator, which means C, D, D, D 40 times for some C and D, under the assumption that there is no cancellation in it, and that C is, say, 16 times bigger than D. And incompatible, I mean that roughly 1/2 of the angle relator could not appear in any place in this mode.
Can you write out this with the compatibility?
This is incompatible.
Right now.
So,
I'm sorry for this.
please,
Incompatible means
namely,
yeah.
roughly 1/2 of the angle relator cannot be a subword of the cyclic word of the cyclic word x, y, z, x, y, z,
Yes, thank you.
So when we have
This is the group.
so let me now remind the combinatorics of the angle relation. So we have C, D, D, D 40 times. So let me say that this is index 0, this is index 1, this index 2, etc. This will be actually 39. So when we have drawn this picture, so these two correspond to the last appearance of D in the angle relators. So these two to the previous one. So this will be east and west. This will be north and south. Now here we have
Are you sure?
north, east, north, west, south, west, south, east. This will be number 2. There are 4 of them.
Are you sure that to the left is east?
Here is east.
Here it is west. It's okay, yeah. Because you're fine.
I think it. So of kind 2 we have 4 of them. Of kind 3 there will be 8 of them. It is to the power 3. Of power 4 will be 16 of them. And you see, the next are oriented toward the previous one. The of kind 3 are oriented towards of kind 2, every place. Now the next one we inserted with them of kind 4, all of them will be oriented towards 3. So there will be this coming for the next one, there will be 16 of them, etc., etc. So this is now in between we have the word C, which will appear 2 to the power 40 times, and its exponent will be also 1, negative 1, 1, negative 1. It will just change this. So this is roughly is precisely the combinatoric of the angle relator. So, what happens? Then we will see that this combinatoric will be of the following form. With the word, we have some power of C, then we have D to the power, say, delta 1, C in the opposite direction, D to the power delta 2, C in the straight direction, D to the power delta 3, etc., etc., etc. Now, when these delta are corresponding to a certain regularity we have described it earlier, and its particular form need not concern us, which is in some way, actually we take the biggest power, the biggest odd power of it. If it is 1 modulo of 4, then it is positive. It is 3 modulo 4, it will be negative, but this is the rule for the signs of delta. Any case. And then we know that actually the beginning of C and the end of C are symmetric. We can assume that C itself is some C prime B plus minus 1 C prime negative 1 in this way, etc. We have this kind of structure, we assume this. Now, and what happens? That here the word D is cyclically reduced. So it means we go in this direction, and this letter is precisely this one. Here is the first instance when this letter is different from the inverse of this letter. This is the place where it is, because the verb that is cyclically reduced. And now I'm saying that this kind of combinatorial structure is incompatible with this. Why? Okay. We actually can assume that just taking many steps, we have that A could be actually a long word. And then it itself will have some occurrences, this A, will have occurrences of the word C and D in a particular signs. Okay. Now, then if this A appears once again in the opposite direction, so all of these words will appear here, the same structure of C's and E's will be here in the other word. Now, we have proven that for the angle relation, every appearance of C is standard. I mean standard, that I mean that in this world, if we look on C, it could appear only when it appears formally here. It cannot be in other places. That we have just strictly proven in one of the previous lectures, and actually it was from the joint work of Ari, Ewers, and Collins. They have proven it and just got to this result. It means that all the appearances of C and then of course of D will be formal, just as they are written here. Then when we look on these two words, So all these appearances of this will be just formal as well. And then we can look on this and see the first place where the symmetry will be broken is this one letter X. And here, for the same reason, the first letter the symmetry broken will be the letter Y. And this is impossible, because in this word, if the symmetry could be broken only on the same word here. Whatever we do, the symmetry should be broken on the word. There may be a bigger word, but it should start and end by the even number of these. Now, and then, but here it should be broken just on one letter. Then it should be just the length of this would be 1, and this D should be on one side, it should be equal to X. On the other side, it should be equal to Y. This is a contradiction. Because the place where the symmetry is broken in this word could be only start with D, because the word is formal, just as written. And so it could be a word, it has an odd number of instances of D. But on the other side here, the symmetry is broken on a single letter. So this should be only one letter in this D. On one side it should be equal to X, on the other side it should be equal to Y, and this is impossible. So we are done in this sense. So, actually, this is just a small part of a bigger phenomena that all these kinds of combinatorial structures are mutually incompatible, when we take different commutators. But this is a kind of a phenomena. I will not go in further discussion about it, but one can just look on it. But this is a simple instance of it, where, because you see what happens with higher combinatorial, there's a kind of partial symmetry. This is abundance of partial symmetries. If we have partial symmetries of different kinds, they could not live together on a big part of it. So, but actually, this is more than we need here. Here we just have the small part of it that we need from this place. So in this sense, explains why we cannot have a nilpotency of any class if we take a Frege group with three generators.
Yeah, last time you explained that the derived map looks as you draw.
Yes, because what I did by induction is that when we have the next derived map, then the region of the smallest round in this derived map, if all the neighbors are all the smallest rounds, they have at least 9 neighbors, actually very much neighbors, and if it has one neighbor of some bigger round and the rest of the same smaller round, then it is at least 5 neighbors of this smallest round. Yes, and this is enough to ensure the convex layer structure of the next derived von Kampen diagram. And we just proceed by induction until we reach the last derived map, and then all the regions of smaller round are exhausted. We have only regions of the highest round present in this map. Then it has each of the many, or at least 9 neighbors of the same round, and then we can inductively apply the idea of the convex layers again. And then we have actually this, which we need, that we have a sufficient criteria when a word is different from one. So this is the way, as we always use the usual or generalized cancellation condition in this sense.
So, yeah, once again, just to finalize. So you take an angle group with 3 generators.
With 3 generators with n equal to 40.
With n equal to 40.
Yes.
Yeah.
With this both C and D, D 40 times equal to 1. Actually 45, but doesn't matter.
And you know, you already proved that should be the one phenomenon of say, good type.
A kind of, exactly, this is a kind of Greenberg lemma. If every word that is equal to 1 in this group must have actually a number of pieces. One can make it precise, but just, we actually doesn't need the full strength of the Greenberg lemma. It could be proven if one needs it, yes, but it's easy thing to see, just make it to around the word, so we have enough pieces, but actually we need only that some relatively big piece of some relator is present in this word. And this is enough for us to be able to show that certain words are different from one, because they do not have instances of subword. It's easy constructed. Particularly, one can take a commutator of arbitrary lengths and show that it never will have such length subwords because of symmetry reasoning.
Incompatible symmetry.
They have incompatible symmetries, therefore this word never could have a big part of the angular relation, so it is different from one in the free angle group.
Then you potent one.
So yes. So in the input we have, so it means that commutators or arbitrary big weight will be different from one in the free angle groups by on three generators.
The reasoning is combinatorial.
Combinatorial? Yes. The argument here is combinatorial. Actually, is a part of a much bigger phenomenon that different combinatorial structures coming from higher commutators are incompatible.
And then there is a contradiction with the phenomenon, so small cancellation phenomenon.
In a sense, this is the standard way to argue within the small cancellation theory. But when we have the sufficient condition for a word to be different from one, we just produce words that satisfy this condition. And the way, by the way, a similar proof was in the Adamowicz paper.
Yeah.
But then they use amplitudic sequences.
This is clear.
Okay, fine. So actually, let me now.
This periodic sequences also possess a kind of symmetry which is
Depends how you produce it. There's a lot of way to produce it. Okay, now let me go to super divisible groups. In a sense, this topic is much easier. But let me. So, this is actually not a difficult topic, but let me nevertheless to refer to it. First, let me recall what is a divisible group. That group G is divisible if for any G in G and N in Z and differable from 0, that is H in G such that H to the power N is equal to G. And then this generalized smoke cancellation technique, it is known. That there are non-trivial, finitely generated divisible groups. I guess also Schansky and other constructed such things, and this construction also proves a generalized smoke cancellation theory. Now, I will continue after the break. What I have to say is that instead of solving this, we can take any word W of x1, x2, xn, and asking the question for a given word G, whether we have such h1, hn, that G, the W of h1, h2, hn is equal to G. Of course, we mean here a non-trivial word.
If you want to get if you generated such a group, not necessarily finally generated.
No, we would like to have, it is easy to construct this group, it is not finitely generated. The point here is that we would like to see a group which is also finitely generated. The whole point is to make it finitely generated.
It is easy to construct a Fisher with such a group instantly generated, but
Yeah, you do if it
I understand, but the question is, does it exist among the real life?
Excuse me?
Does it exist among the real life?
In what?
Real life.
No. Outside the, no, it is only in the laboratory.
No, I guess that this group can be in real life as well.
Never observed it.
PSL2 over a field.
Maybe, but we have to prove it yet.
I don't know.
Okay. So let me make now a break, and then we will reserve it. And actually, this is unlike the Engel group, it's easy construction.
Okay.